what the heck are convolutional neural networks? If you're not in the machine learning world, these might seem like a new idea to you. So let me go through some examples of some problems you might use them to solve first. If you want to have an image and you want to know what is the primary object in this image, this is a task called image classification. And obviously this image on the left here, this is clearly a dog. This image in the middle, this is clearly a cat. This one on the right, there might be some debate of whether it is a banana or it is in fact a cat. And you would like some sort of algorithmic system to take in these input pixel values and spit out some probabilities for dog, cat, banana, a whole bunch of other classes, whatever you have. Well, a convolutional neural network, or any kind of machine learning system in general, will do such a thing. But a CNN, the way it works is create what's called a small filter. So think of just like a 5x5 window. And you're going to look at just a small 5x5 window of your image at a time, and you'll take some weighted average of all those pixels across whatever the colors are. You'll use that to compute some new pixel value in sort of a hypothetical new filtered image. You do that in one pixel, then you move your window over, you use take the same type of weighted average, compute the next pixel, so on and so forth, dragging this filter across the whole image. These weights are things that we're going to try to need to learn later. But the point is, that gives you one sort of filtered image. You can use a different set of weights to get a different filtered output. And then once you have all these new filtered outputs, well, that's just like having a new image, except instead of maybe having 3 colors, now you have like 10 or 20 or 40, however many filters. If you put that through some sort of nonlinear function, and then you have a new image, and you can now take a filter of those filtered images. And that creates another layer of your convolutional neural network. You can do this again and again and again. There's a few other steps I'm glossing over. But this lets you build up sort of higher and higher level features in your image. And at the very end, you'll do what's called logistic regression. You can think of it as a fancy least squares that will let us predict probabilities at the very end. And there might be a few things in between. The point being, if you have a bunch of images and you know what the labels are, for example, dog, cat, whatever, you can train these weights. You can figure out what the weights are on all these different filters. You generally start with some sort of random initialization, and you'll do a general simple gradient descent kind of optimization procedure like we've done in class. Okay, but let me zoom back out for a second. How does it really work? When you put your image in, your bunch of pixels, however big it is, it goes into your convolutional neural network, and it spits out a vector of probabilities, one for each class. And if you try to imagine, like, well, what is it really doing? It's got these filters here. You can just look at those filters and understand, one layer of filters, okay, this one's kind of looking for edges, this one's looking for particular shapes. A second layer of filters, now it's a filter of filters, and maybe you can keep track of a couple of filters in your head, but it becomes very difficult to understand what's going on. And if you have even more layers, it's almost impossible. So something you can try to do is like, well, I'll just try different inputs and I'll see what I get. If I put in my pictures of cats, do I actually get cats? And this kind of leads into one general idea that I like to call idealization, of what is the most cat-like image that I can possibly put into my model. So you can think is, I want to optimize and find the most cat-like image, and maybe I just look through my training corpus and here say, oh, okay, this middle picture, 0.99, that's the highest probability of cat that I've gotten. So I think that's my most cat-like image. But that's the most cat-like real image. What if I can make a synthetic image? And in fact, I'm going to flip this optimization process on its head, whereas before, I was optimizing for those weights. Now, for a given set of weights that I've obtained, however I've gotten them, I will fix those, and I will optimize the input to maximize the probability of cat. Or maybe I'll look at some filter in the middle, and I just want to maximize whatever that's giving me. And this is sort of very simple. You'll recognize this as a forward Euler iteration here. And you can actually do this, and you can generate a synthetic image. So in this case, I took a pre-trained model called ImageNet that has like 1,000 different classes, picked one of the classes sort of at random, and I said, sure, show me what the idealization, the Platonic ideal of whatever this class is. And you get this kind of gray, trippy picture. If you look real closely, you can kind of see maybe some eyeballs, maybe some like fins, things that look sort of like wings. This is actually like a kind of goldfish class. And you can sort of agree, okay, the model is kind of finding real things, but this doesn't look like a real image at all. And this is just giving me general information about the network for a specific class. What you might want to know, however, is something more along the lines for a specific image. I don't have time to talk about this particular image, so we'll go on, but this is just looking at different idealizations for different filters. Okay, there's a cool idea called deconvolution, where it says, I want to find, for a given image, what part of this image, what about this image, most contributed to like the idea of cat. So you might imagine from this image, I'd want to like black out all this carpet and all this other nonsense and just focus on the cat, and maybe this banana doesn't really contribute. Something like that. So can we build an image out of only the most cat-like components? And we're going to, again, I want to stress this is distinct from before. We're going to obtain image about a specific input, one specific image at a time, and for a specific class in this case. So this idea is called deconvolution. It was put together just a few years ago, forever in the machine learning world. And the idea is, somewhere in your network, maybe at the very end, you're computing, cat or whatever, I'm going to zero out everything else. So as though, pretend I had gotten to some point where I had a maximum value of cat. And then I will try to invert the process to see what input would have gotten me to that point. There's a problem in that you can't perfectly invert. One, due to the nonlinearities, and two, there's information you're sort of losing, and you're spreading out. You're spreading out information spatially and gaining it in other ways. So you can only pseudo-invert this, but you can do it, and you can get backwards through all your layers to try to see what image would have gotten me to this maximally activated case. And I did one example where I picked a random image I had of me on vacation one year, and I ran it through and I said activate a particular filter. And for that particular filter, this wasn't cat or bird or whatever, but we can see it tended to highlight all of these little like crescent shapes, which I found very, very interesting. But it's kind of gray, washed out. It finds things all over the image that are generally totally irrelevant. You would probably say this is an image of a person or a bird or maybe a building. But we kind of find everything. So it's not ideal still. Similar to before, I don't really have time to talk about this image, but you can do this to any given filter in your image, and you can try to see what is this filter finding in this particular image. Okay, so those two approaches sort of work, but they tend to activate everything, and it's just the overall gray. This is difficult for a human being to understand, and the point of our project was to help understand through visualizations how is this convolutional neural network really working. So maybe instead of trying to find like what, we can instead just focus on where is interesting, where is relevant. So if your model has a very particular structure, that is, it is fully convolutional up until the very end, you can do what's called a class activation mapping, where you can sort of look at the weights at the very end in that final layer, just before you compute those probabilities, and you can convert them into a heat map that shows what parts of your image most contributed to a particular class. So you can see they do this sort of thing like here, they look for dog, and they say, oh, this particular filter doesn't contribute much to dog, this one does, the other ones do. You take a weighted sum of those, and then you get a nice picture like that. There's a problem. Most models don't have this particular structure. If you were making a new model, that's great, you could do that. But what if you just have a model that someone handed you and you want to understand how it works? Then this doesn't work. So what we can do is we can approximate that special structure by computing the gradient, that is sort of taking a first derivative approximation to the final convolutional layer and the output. So there'll be some stuff in between, but we don't really care about that. We're just going to take the gradient between those things, and now we can use that value and do the same class activation mapping. And if you actually have that special structure, this is the same thing. So it's actually kind of nice. It's a generalization of that technique. And again, if you can compute your actual activation this way, the same kind of weighted sum. There's a lot of details I don't have time to go into, unfortunately. But this gives you the same kind of image. But now you can apply it to a much broader class of models, essentially anything with a convolutional backbone like this. Here's some images I took from the paper that proposed it. Here, they're activating where does cat activate? And you can see primarily it's on the cat. In this case, it's actually on the stripes because it's a very specific type of cat. Don't really have time to get into that. It kind of activates in other places, but not so much. And on this picture on the right, it's where it's activating for dogs. So if you wanted to say, for my specific model, for this specific input, for this specific class, where are we seeing things? And this, they make an important point. This helps human beings understand how does that model work. And this helps human beings build trust and say, yes, I believe this model is doing the right thing because it told me this was a dog, and where it thinks it's a dog is in this general location. So that's an interesting point that isn't often as directly accounted for. But this gives us very specific types of information in an easily digestible format. So GradCam, and it's a little more recent, does seem like a pretty useful tool in general. Some other things I didn't get to, but I would love to start looking at. You can do an adversarial attack, so where someone tweaks your image slightly in order to make your model spit out completely wrong answers. And if you could imagine doing that in something like this, you might expect that the heat map, if you tweak this to look like spaceship, but human being wouldn't tell the difference, it might look totally wacky in the heat map. Well, it turns out you can also tweak it in a way that fools GradCam as well, by essentially tweaking just the right kind of pixels. But that's an interesting idea and a way to evade visual detection. These are all sort of input-specific visualizations. If we could have something sort of like the idealization process, but for a specific image, that's sort of like a general GradCam, but that doesn't really work. Just better ideas for network-level visualization, I think, would be very interesting. And better generalization of these cam-like approaches. These are sort of heuristically driven. There are some more recent papers that are trying to ground these in sort of like eigenfunction bases kind of things. And if you've seen singular value decomposition of like faces, images of faces, that sort of takes a similar idea, but trying to apply it to this class activation mapping. I've only seen some of that. I haven't delved into it super deep, but I think that would be very interesting. Yes, and that is what I have on class activation mappings. So thank you very much. Hopefully that talk wasn't too fast, and we'll find out on the stream. Thank you.